Far beyond Neptune, beyond Pluto, and even beyond the reach of the solar wind, the Sun's influence continues into a vast and almost invisible realm. This is the Oort Cloud, a distant reservoir of ancient ice and rock that may stretch nearly halfway towards the nearest stars. It is so enormous that Voyager has barely begun the journey toward it. Tonight, the journey moves from interstellar darkness inward to discover where the solar system truly ends. If peaceful journeys through space help make the night a little calmer, please like the video, subscribe to the channel, and settle in as the voyage begins. At the farthest reaches of the solar system, the Sun no longer dominates space in the simple way it does near the planets. Its gravity still extends without a hard stopping point, because gravity weakens continuously rather than ending at a fixed wall. Yet there is a practical frontier where objects can remain bound to the Sun only very loosely, and where the wider gravitational field of the Milky Way becomes increasingly important. This remote region lies so far from the Sun that sunlight is extremely faint. Orbital periods stretch across millions of years, and even small gravitational disturbances can gradually reshape a body's path. The boundary is therefore not a surface that could be crossed in a single instant. It is a broad transition in which solar gravity, galactic gravity, and the influence of passing stars compete over immense spans of time. The Sun moves through the Milky Way as one star among hundreds of billions. It follows an orbit around the galactic center, while neighboring stars move on their own paths through the same disk. The solar system travels inside this changing stellar environment, and its most distant, gravitationally bound objects experience forces that are almost negligible on human scales, but significant over geological time. A small icy body close to the Sun is held firmly by solar gravity. A similar body at a distance of tens of thousands of astronomical units is held far more weakly. At such distances, the difference between remaining attached to the Sun and drifting away into interstellar space can depend on very slow changes accumulated over millions or billions of years. Astronomers often describe the Sun's outer gravitational domain using the idea of a hill region. In a simplified sense, this is the volume within which the Sun can retain objects against the larger gravitational influence of the galaxy. The real situation is more complicated than a perfect sphere, because the Milky Way has structure. The Sun moves through the galactic disk, and nearby stars occasionally pass at varying distances. Even so, the concept helps define the scale involved. Estimates place the Sun's effective gravitational reach at roughly 1 to 2 light years, although the exact value depends on how the boundary is defined and on the direction considered. A light year is the distance light travels in 1 year, so even this outer limit remains only a small fraction of the distance to the nearest stars. At these extreme distances, the Sun appears less like the overwhelming center of a planetary system and more like a bright star surrounded by an enormous, nearly empty gravitational domain. The energy received from sunlight, falls with distance, and temperatures in small, isolated bodies remain very low. Their surfaces can preserve frozen compounds that would evaporate much closer to the Sun. Water ice, carbon dioxide ice, carbon monoxide ice, methane, and other volatile materials can remain stable for long periods, depending on an object's composition and exposure history. Yet the environment is not perfectly unchanged. Cosmic radiation, occasional energetic particles, collisions with tiny grains, and slow thermal processing can alter exposed surfaces over time. The Milky Way produces a weak but persistent tidal force across the solar system. Galactic tides arise because the gravitational pull of the galaxy is not exactly identical at every point around the Sun. The difference is extremely small across planetary distances, but across distances approaching a light year it becomes more important. A distant object can therefore experience a gradual change in the shape or orientation of its orbit, even while remaining associated with the Sun. These changes do not usually occur as sudden events. They accumulate slowly, orbit after orbit, under a gravitational influence that is gentle but continuous. Passing stars create another source of disturbance. Most stellar encounters are distant and have little immediate effect on the planetary system. At the solar system's remote gravitational edge, however, a star passing within a few light years can slightly alter the velocities of weakly bound objects. Over the age of the solar system, many such encounters occur. Some remove bodies from solar control, others change orbital directions or distances without unbinding them. The outcome depends on the passing star's mass-speed trajectory and distance, as well as on the original orbit of the small body. Because encounters occur irregularly, the outer boundary of the Sun's domain changes gradually over time rather than remaining fixed. The galactic environment also changes as the Sun travels through the disk. The density of stars and interstellar matter is not uniform everywhere. The Sun's path carries it through regions with somewhat different local conditions, though the details of its past galactic environment cannot be reconstructed perfectly. This uncertainty matters because the most distant bound bodies respond to very weak external forces over very long intervals. Their present arrangement is therefore shaped not only by the Sun, but also by the history of the solar system's motion through the galaxy. No spacecraft has directly mapped this gravitational frontier. Voyager 1 and Voyager 2 have crossed the heliopause, where the solar wind gives way to the interstellar plasma, but that boundary lies vastly closer to the Sun than the outer gravitational limit considered here. The distinction is important. The heliopause marks the effective edge of a flowing atmosphere of charged particles from the Sun. It does not mark the end of solar gravity. Far beyond the heliopause, an object can still travel on an orbit controlled mainly by the Sun, even while moving through interstellar gas and magnetic fields. The true outer edge of the solar system is therefore best understood as a region of diminishing attachment rather than a line. Close enough to the Sun, gravity clearly maintains long-term orbital control. Far enough away, galactic tides and passing stars can remove objects with increasing ease. Between those conditions lies a broad, uncertain frontier, whose position changes with time and direction. The scale is immense, the material is sparse and direct. Observation remains difficult. What defines this region most clearly is not visible structure, but the balance of gravity itself, with the Sun holding its most distant companions only faintly against the larger gravitational landscape of the Milky Way. Across this boundary, distance becomes less important than stability, because an orbit may remain solar for ages before a disturbance changes it. At the outermost fringe of the Oort Cloud, the solar system becomes extraordinarily sparse. The Sun still holds some icy bodies in long, slow orbits, but the grip is weak and easily disturbed compared with the firm control it exercises over planets and objects much closer inward. This distant population is not observed as a glowing shell or a visible ring. Instead, its existence is inferred mainly from the orbits of long-period comets that arrive from many directions. Their paths suggest a vast reservoir surrounding the Sun at distances measured not in millions of kilometers but in thousands and tens of thousands of astronomical units. An astronomical unit is the average distance between Earth and the Sun. At the outer fringe of the Oort Cloud, a single object may travel tens of thousands of such distances from the Sun. Light itself can require many months to cross part of this region. A small icy body there completes one revolution only after enormous intervals, often taking millions of years. During most of that orbit, it moves very slowly because it is far from the Sun and receives only a faint gravitational pull. The familiar rhythm of planetary motion gives way to an almost motionless scale in which a body can spend nearly all of recorded human history, shifting only a small fraction of its path. The exact outer extent of the Oort Cloud is uncertain. Estimates commonly place its remote regions at tens of thousands of astronomical units, with some definitions extending toward about 100,000 astronomical units or somewhat farther. No sharp edge separates cloud members from interstellar objects. Instead, the number of bodies is expected to decline gradually as distance increases and as the Sun becomes less able to retain them. Near the extreme fringe, long-term orbital stability becomes fragile. A body can remain associated with the Sun for vast periods and still be vulnerable to a weak disturbance that would have little effect on an object nearer the planetary system. The outer fringe is expected to be roughly spherical rather than concentrated in a thin plane. This shape differs from the flattened arrangement of the major planets whose orbits mostly remain close to the same broad plane around the Sun. The distant cloud is thought to contain bodies moving on highly tilted paths in many directions. Some may orbit in the same general sense as the planets, while others may travel on paths that appear reversed when compared with planetary motion. Such a distribution is consistent with a population that has experienced gravitational scattering and long-term perturbations over the age of the solar system. Individual objects in this distant region are probably small and dark. Many are expected to contain mixtures of frozen water carbon compounds, silicate rock and other materials inherited from the early solar system. Their surfaces receive little sunlight, so reflected light becomes extremely weak by the time it returns toward telescopes near Earth. Even relatively large objects would be difficult to detect directly at these distances. This observational limitation is one reason the Oort Cloud remains an inferred structure rather than a mapped population. Astronomers can study comets after their orbits carry them closer to the Sun, but the remote reservoir from which many of them originate remains largely unseen. The density of material in the outer fringe is extremely low, although the Oort cloud may contain a vast number of objects. They are spread through an enormous volume. The average separation between neighboring bodies is therefore expected to be large. Collisions are likely to be uncommon compared with the crowded conditions that existed when planetesimals first formed near the young Sun. A body can travel for immense periods without passing near another cloud object. The region is better understood as a dispersed population sharing a broad gravitational domain than as a compact cloud in the everyday sense. Solar heating is also very weak. At such great distances, sunlight provides little energy to warm exposed ice. The temperatures of isolated objects remain extremely low, although exact values depend on composition, surface reflectivity, rotation, and the faint background of radiation from space. Volatile substances can remain frozen for very long periods. When one of these bodies is eventually redirected onto an orbit that carries it close to the Sun, heating can release gas and dust, producing the visible activity associated with a comet. While it remains in the outer fringe, however, it is expected to stay largely inactive and difficult to distinguish from the darkness around it. The weakness of solar gravity at these distances allows external forces to become significant. The gravitational field of the Milky Way changes slightly across the scale of the cloud, producing a gentle tide that can alter an orbit over long intervals. Nearby stars also pass through the broader galactic neighborhood and can produce temporary changes in the motion of distant bodies. Most of these influences are small, but the long orbital periods of outer cloud objects give such perturbations time to accumulate. Some bodies can be shifted onto paths that bring them closer to the Sun, while others can be pushed outward until they are no longer securely bound. This slow reshaping means that the outer fringe is not a permanent collection of objects occupying fixed places. It is a dynamic population evolving on time scales far longer than a human lifetime. Objects can enter more stable or less stable trajectories, and some can escape into interstellar space. Others may remain bound through much of the solar system's history. Statistical models rather than direct inventories are therefore used to estimate how many objects might occupy this remote volume and how their orbits change. The outermost Oort fringe marks one of the largest structures associated with the Sun. Its scale is defined by distance, but its character is defined by weakness, faint sunlight, slow motion, rare encounters, and delicate gravitational attachment. The bodies there remain part of the solar system only because the Sun continues to influence their paths more strongly than competing forces over long periods. At the edge of that control, the cloud becomes thinner and less stable, fading gradually into the surrounding galactic environment without a visible boundary. Here the solar system does not end abruptly. It becomes progressively less secure as ownership weakens across enormous distances. Within the extreme outer Oort cloud, the Sun still governs the motion of countless icy bodies, yet its control is fragile enough that the galaxy itself becomes part of their orbital environment. These objects occupy paths so large that a single journey around the Sun can extend across millions of years. Their orbits are often highly elongated, carrying them through regions where solar gravity is weak and where small external forces can slowly alter their directions. Nothing in this region moves quickly by planetary standards. Change accumulates through repeated, almost imperceptible adjustments, and the architecture of the cloud reflects this patient interaction between the Sun and the surrounding Milky Way. The most important large-scale influence is the galactic tide. This tide does not behave like an ocean wave. It arises because the gravitational pull of the Milky Way varies slightly across the enormous volume occupied by the outer cloud. The Sun and a distant comet are both moving through the galaxy, but they do not experience exactly the same pull from the galactic disk and the mass distributed around it. The difference is tiny, yet over immense periods it can change the orientation and shape of a cometary orbit. A body that once remained far from the planetary region can gradually acquire a path with a smaller, closest approach to the Sun. The effect is strongest for objects that travel very far outward because solar gravity weakens steadily with distance. Near the planets, the galactic tide is insignificant compared with the Sun's attraction. In the extreme outer cloud, the balance changes. A comet near the distant end of its orbit moves slowly and is only loosely bound, giving weak external forces more time to influence its motion. The tide can gradually alter the direction of the orbit and change the distance of the comet's closest return. These shifts remain small from one moment to the next, but their cumulative effect can become important over millions of years. Passing stars add another layer of change. The Sun does not move through an empty galactic neighborhood. Other stars pass at different distances and speeds, each producing a temporary gravitational disturbance. Most remain far enough away that their effects on the planetary system are negligible. In the outer Oort cloud, however, even a distant stellar passage can slightly change the velocity of weakly bound objects. A single encounter rarely rearranges the entire cloud, but repeated encounters over the age of the solar system contribute to a continuing redistribution of distant orbits. The strength of a stellar disturbance depends on several factors. A more massive star produces a stronger gravitational effect than a less massive one at the same distance. A slower passage generally allows more time for gravity to act, while a closer passage increases the disturbance sharply. The position of an Oort cloud body at the time of the encounter also matters. An object on one side of the Sun can be pushed differently from another body in a different direction. Because the cloud extends around the solar system, each stellar encounter affects a complicated three-dimensional population rather than a simple ring. Some disturbances increase orbital energy enough to loosen an object's connection with the Sun. If the change is sufficient, the body can escape permanently and continue through interstellar space. Other disturbances reduce or redirect orbital energy and leave the body bound. A comet can also be shifted onto a path that eventually carries it much closer to the Sun. The outer cloud therefore acts as a region where the distinction between stable membership and eventual escape is continuously tested by weak forces operating over long time scales. Long-period comets provide the strongest observational evidence for these distant processes. When such a comet approaches the inner solar system, astronomers can determine its orbit from repeated observations. By reconstructing that orbit backward, they can estimate how loosely the comet was bound before planetary encounters and solar heating altered its motion. Many long-period comets arrive on paths consistent with origins at enormous distances. Their orbital directions are widely distributed across the sky, supporting the idea of a roughly spherical reservoir rather than a flat disk. Even these observations carry uncertainty. A comet observed near the Sun has already entered a region where planets can perturb its orbit and gases released from its surface can produce small non-gravitational forces. Reconstructing its earlier path therefore requires careful modeling. The distant cloud itself is not directly visible as a complete population. Scientists infer its structure statistically from the comets that become observable and from computer models of gravitational evolution. Those models indicate that galactic tides and stellar encounters are natural mechanisms for sending some distant bodies inward while removing others from the Sun entirely. The outer cloud also preserves evidence of the solar system's long residence within the Milky Way. Its members are not isolated from galactic history. Their present distribution reflects billions of years of changing stellar surroundings, repeated distant encounters, and continuous galactic tides. Some objects may have survived since the early solar system, while others may have been lost. It remains uncertain exactly how many bodies occupy this region, how their numbers vary with distance, and how strongly past stellar environments have altered the original population. Despite these uncertainties, the governing physics is clear. Solar gravity establishes the orbits while the wider galaxy slowly modifies them. At extreme distances, the distinction between a closed system and its environment becomes less sharp. The Sun remains the central mass, but it does not act alone. Every distant body travels within both a solar and a galactic gravitational field, and its path records the combined effect of those forces. The extreme outer Oort cloud is therefore a region of quiet orbital sensitivity. Its icy bodies can remain nearly unchanged in appearance, while their trajectories evolve over spans far longer than civilizations or species. Their motion is slow, their spacing is vast, and their stability is conditional. In this remote volume, the solar system is shaped not only from within, but also by the faint, persistent gravity of the galaxy through which it moves. A slight change in velocity near the farthest point of an orbit can accumulate into a major alteration in the body's next return, showing how sensitive these distant trajectories remain to gravity. Farther inward from the most weakly bound reaches of the Oort cloud, distant icy bodies remain exposed to passing stars, but the balance of forces begins to shift more clearly toward the Sun. Solar gravity is still faint compared with conditions near the planets, yet it is strong enough that many objects can retain their orbits through disturbances that would more easily remove bodies from the outermost cloud. This region is not separated by a sharp boundary. It is a gradual zone in which stellar encounters continue to matter, while the long-term stability of solar orbits becomes somewhat greater. Each passing star produces a gravitational influence that changes with distance. The effect is strongest when a star approaches relatively close to the solar system, but even then the disturbance weakens rapidly across smaller and more tightly bound orbits. Bodies in this region, therefore, respond less dramatically than objects farther away. Their paths may be tilted, stretched, or slightly redirected. Yet many remain bound to the Sun, because their orbital energy is lower and their attachment is stronger, a stellar passage that can remove some objects at the edge may only adjust the trajectories of those deeper inside. The solar system has experienced many stellar encounters over its history. Most are distant and gentle, producing no obvious effects on the planets. At Oort cloud distances, however, their cumulative influence becomes part of the long-term evolution of the population. A star can pass through the galactic neighborhood over tens of thousands of years, exerting a slowly changing pull as it approaches and recedes. The result depends not only on the star's mass and speed, but also on the location of each icy body along its immense orbit. Because these bodies occupy three-dimensional paths, the same encounter can have very different outcomes across the cloud. One object may receive a slight increase in orbital energy, another a decrease, and another mainly a change in direction. A body near the farthest point of its orbit is especially sensitive because it moves slowly there and remains under weaker solar control. A similar object closer to the Sun along the same orbit is harder to disturb. The structure of the cloud therefore changes unevenly shaped by the timing and geometry of each encounter. The Sun's own motion through the Milky Way also influences how these encounters occur. Nearby stars do not remain fixed around the solar system. They move through the galactic disk on independent paths, so the pattern of stellar passages changes continuously. Over billions of years, some stars pass closer than others, while many remain too distant to matter significantly. The exact sequence of ancient encounters cannot be reconstructed completely, leaving uncertainty about how much of the present Oort cloud reflects its original structure and how much has been rearranged. Computer simulations help scientists examine these possibilities. In such models, large populations of small bodies orbit the Sun, while the gravitational effects of the galaxy and passing stars are added over long periods. The simulations show that the more tightly bound parts of the cloud are generally more resistant to stripping than the outermost regions. They can survive numerous weak encounters while still experiencing gradual changes in orbital inclination, eccentricity, and orientation. Eccentricity describes how stretched an orbit is compared with a circle. In this region, many orbits remain highly elongated even when their exact shapes evolve. Some stellar passages can send objects toward smaller distances from the Sun. The change does not require a dramatic collision or close approach between stars and comets. A tiny adjustment in velocity can be enough to alter the next stage of an orbit that lasts millions of years. If the closest point of an orbit decreases, the body may eventually enter regions where other gravitational influences become more important. Within the stellar disturbance zone itself, however, the key process remains the slow modification of distant orbits by stars that pass through the surrounding galactic environment. Other objects move outward after an encounter. A disturbance can raise the farthest point of an orbit or weaken the body's binding to the Sun. In many cases, the object remains part of the solar system, but its future path becomes more vulnerable to later encounters. Repeated small changes can accumulate gradually, moving a body between more stable and less stable states. This makes the population dynamic even when individual objects appear frozen and inactive for immense intervals. The probability of major change also depends on how often close stellar passages occur. In the present galactic neighborhood, truly close encounters are uncommon, but the age of the solar system provides enormous spans of time for rare events to accumulate. A strong passage can leave effects that persist long after the star has moved away. The surviving orbits then become starting conditions for later disturbances, allowing the cloud to retain a memory of encounters that can no longer be observed directly. The material itself remains cold and mostly unchanged by sunlight. At these distances, solar radiation is weak, and the icy surfaces of small bodies can preserve volatile compounds for extremely long periods. Their physical evolution is therefore much slower than their orbital evolution. Gravity changes where they travel while their surfaces may remain nearly dormant. Cosmic rays and energetic particles can alter the uppermost layers, but the overall body can preserve ancient material from the early solar system. Direct observations of this region remain limited. Telescopes cannot easily detect small dark bodies so far from the Sun, and no spacecraft has reached these distances. Scientists instead study the orbital distribution of long-period comets and compare it with dynamical models. Those models indicate that passing stars are important but not equally effective everywhere. Their influence becomes progressively weaker relative to the Sun as distance decreases. The stellar disturbance zone, therefore, represents a transition in orbital security. The Sun is no longer holding its companions with the extreme delicacy found at the cloud's farthest edge, yet the surrounding galaxy still leaves a measurable imprint on their paths. Each body moves through a quiet, gravitational landscape shaped by two scales, at once the local pull of the Sun and the changing presence of nearby stars. Over millions of years, their combined influence slowly edits the architecture of the cloud without producing a visible boundary or sudden transformation. Deeper within the Oort Cloud, the broad gravitational influence of the Milky Way continues to act on distant icy bodies, but the Sun holds them more securely than it does near the outermost fringe. The most persistent external force in this region is the galactic tide, a gradual difference in gravitational pull across the immense volume surrounding the Sun. The effect is weak at any single moment, yet it remains present over millions of years. For bodies that travel on enormous orbits, this steady influence can slowly change the shape, tilt, and orientation of their paths without removing them from the solar system. The galactic tide arises because the Milky Way is not a point mass. Its stars gas dark matter, and central regions create a distributed gravitational field. The Sun and a distant comet both move through this field, but they do not experience exactly the same acceleration. The difference is small, though over a distance of many thousands of astronomical units, it becomes dynamically important. A comet far from the Sun can therefore feel a slight pull that differs from the pull acting on the Sun itself. Over long intervals, this difference modifies the comet's orbit. The strength and direction of the tide depend partly on the structure of the galaxy around the solar system. The disk of the Milky Way contains much of the local, visible mass, so the vertical pull toward the galactic plane is especially important in models of Oort Cloud evolution. There are also weaker components associated with motion toward and around the galactic center. Together, these forces create a slowly changing background that acts continuously while the Sun travels through the galaxy. For an individual icy body, the most noticeable consequence is often a gradual change in perihelion distance. Perihelion is the point in an orbit closest to the Sun. A body whose perihelion remains extremely distant may spend its entire existence far beyond the planets. Under the influence of the galactic tide, that closest point can slowly shift inward or outward. The process is not regular in the simple sense of a clock. It depends on the orientation of the orbit and on how the body moves relative to the galactic gravitational field. Because the orbital periods are so long, even a slow change can become important. A comet may spend millions of years completing one revolution around the Sun. During that time, the galactic tide acts continuously. Near the farthest point of the orbit where the comet moves most slowly and solar gravity is weakest, the external influence has more opportunity to alter the path. A tiny change there can produce a much larger difference in where the comet travels when it later returns towards the Sun. The tide can also rotate the orientation of an orbit. The long axis of an elongated cometary path does not remain permanently fixed in space. Over many orbital cycles, the surrounding galactic field can alter its direction and inclination. Inclination describes how strongly an orbit is tilted relative to a chosen reference plane. In the distant cloud, such changes help maintain a broad three-dimensional distribution rather than forcing bodies into the flattened arrangement seen among the major planets. This influence does not act identically on every object. Some bodies occupy orientations that make them more sensitive to changes in perihelion, while others respond mainly through shifts in inclination or orbital direction. The exact evolution depends on distance, orbital shape, and the body's position within its long path. As a result, the galactic tide does not move the entire cloud inward or outward together. It slowly rearranges individual trajectories across a vast population. The Sun remains the main source of gravity for these objects. The galactic tide modifies solar orbits rather than replacing them. A comet continues to follow a path centered on the Sun, while the shape of that path changes gradually under the wider galactic field. This distinction is important because the Oort Cloud is not simply floating material carried by the Milky Way. It is a solar population embedded within a larger gravitational environment. Over billions of years, the tide contributes to the movement of some distant comets towards smaller perihelion distances. When this happens, a body that once remained far from the planetary region can eventually enter a path where the Sun's heat and the gravity of the planets become more significant. Other bodies experience the opposite change, with their perihelia moving farther outward. Within the galactic tide region itself, these outcomes remain part of a slow cycle of orbital evolution rather than a sudden migration. The tide also works alongside stellar encounters, though its character is different. A passing star creates a temporary disturbance that strengthens and then fades as the star moves away. The galactic tide is persistent. Its direction and strength change only gradually as the Sun moves through the Milky Way. This continuous influence can therefore shape distant orbits even during long periods when no unusually close stellar encounter occurs. Scientists study this process through numerical models that follow large populations of test bodies over the age of the solar system. These calculations show that galactic tides can help explain why some long-period comets eventually reach the inner solar system from distant reservoirs. The models also indicate that the effect varies with orbital distance becoming much stronger for bodies whose paths extend far from the Sun. Exact results depend on assumptions about the local galactic mass distribution and the history of the Sun's motion. Uncertainty remains because the distant cloud has not been directly mapped. Astronomers observe only a small fraction of bodies after their orbits carry them much closer to the Sun. From those arrivals, they reconstruct likely earlier paths and compare them with simulations. The evidence supports a major role for galactic tides, but the precise structure and population of this region remain imperfectly known. Within this broad zone, the Milky Way acts less like a distant background and more like a quiet participant in solar system dynamics. Its gravity does not overwhelm the Sun, yet it steadily adjusts the paths of bodies that travel far enough away. The result is a region shaped by patience rather than sudden force, where an orbit can change substantially only after immense intervals of gentle, repeated gravitational influence. Within the main spherical reservoir of the Oort Cloud, the solar system takes on a form different from the arrangement of planets. The major planets travel close to a shared plane, but the distant icy bodies in this region are thought to surround the Sun in many directions. Their orbits form a three-dimensional population rather than a thin disk. This spherical structure is not seen directly. It is inferred from the paths of long-period comets which arrive from scattered directions across the sky and often follow orbits that extend tens of thousands of astronomical units from the Sun. The word cloud can suggest a continuous mist, yet this region is expected to contain isolated, solid bodies, separated by immense distances. Each object may be only a few kilometers or tens of kilometers across, though larger bodies may also exist. Between them lies almost empty space. The total population is uncertain because the objects are too faint and remote to count directly. Estimates vary widely, but models generally allow for hundreds of billions or even trillions of comet-sized bodies distributed through this enormous volume. Their combined mass is more difficult to determine because the size distribution remains poorly known. The spherical form develops from the long gravitational history of the solar system. Objects in this reservoir occupy orbits with a wide range of inclinations. Some move close to the plane of the planets, while others pass far above or below it. Some travel around the Sun in the same general direction as the planets, while others move in the opposite sense. This diversity differs from the ordered structure of a disk and indicates that the orbits have been strongly reshaped since the bodies first formed. Although the cloud is spherical in a statistical sense, it is unlikely to be perfectly uniform. The density of objects probably changes with distance from the Sun, and the distribution may contain irregularities produced by early planetary scattering, galactic tides, and stellar encounters. A perfectly smooth shell is therefore not expected. Instead, the region is better described as a vast population whose overall geometry approaches a sphere when considered across large scales. The strongest observational evidence comes from long-period comets. These objects usually have orbital periods longer than 200 years, and many require thousands, tens of thousands, or even millions of years to complete a single circuit. When such a comet enters the inner solar system, astronomers measure its position repeatedly and calculate the orbit that best matches its motion. The observed path can then be corrected for the gravitational effects of the planets and other influences. From this information, scientists estimate the comet's earlier orbit before its close approach to the Sun. Many of these reconstructed paths have extremely large semi-major axes. A semi-major axis is a measure of the overall size of an orbit. For a highly elongated cometary path, it represents half the distance across the longest dimension of the ellipse. Very large values indicate that the comet spends most of its existence at enormous distances. The clustering of many long-period comet orbits at such scales helped motivate the idea of a distant reservoir surrounding the solar system. The arrival directions of these comets are equally important. If the source population existed only in a flat disk, the incoming paths would tend to reflect that geometry. Instead, long-period comets approach from many inclinations, including steeply tilted and retrograde trajectories. This distribution supports the presence of a broadly spherical source. Individual comets do not prove the structure by themselves, but the statistical pattern across many observed objects provides evidence for a three-dimensional reservoir. The observable comets represent only a tiny sample of the bodies that may inhabit this region. Most objects remain far from the Sun throughout their orbits and never become bright enough to detect. A comet becomes visible mainly when its path carries it inward, where sunlight warms surface ice and releases gas and dust. The surrounding material forms a coma, a diffuse atmosphere around the nucleus, and can produce tails that extend away under the influence of sunlight and the solar wind. In the distant reservoir, the same nucleus remains cold, dark, and nearly invisible. This difference between the hidden population and the visible sample introduces uncertainty. Astronomers must infer the number and distribution of unseen bodies from the small fraction that reaches observable distances. Selection effects matter because some comets are easier to discover than others. Bright objects, favorable approaches, and certain orbital geometries are more likely to be recorded. Surveys attempt to account for these biases, but the total population remains uncertain. The main spherical reservoir also contains a record of early solar system dynamics. The bodies are thought to have formed much closer to the young Sun among the region where the giant planets were assembling. Gravitational encounters with those planets scattered many small bodies onto highly elongated paths. Some escaped the solar system entirely, others reached great distances while remaining bound. External gravitational influences then altered their orbital directions, gradually producing a more isotropic distribution. Isotropic means broadly similar in all directions. The present cloud is therefore not simply a collection of objects formed where they now reside. Its structure reflects transport scattering and long-term orbital evolution. The individual bodies may preserve primitive material, but their present locations are products of gravitational history. This distinction helps explain why the cloud can be nearly spherical, even though the planets and the disk from which they formed remain comparatively flat. Across the main reservoir, distances are so large that ordinary comparisons become difficult. A comet can travel through an orbit extending across a significant fraction of a light year, while remaining gravitationally associated with the Sun. Its motion may be only weakly altered during a single human lifetime, yet over millions of years the path can evolve substantially. The cloud's apparent stillness therefore hides a slow, dynamical system. The main spherical Oort reservoir is defined by this combination of vast, scale-sparse matter, varied orbital directions, and indirect evidence. It surrounds the Sun without forming a visible shell, and its existence emerges from the repeated arrival of long-period comets from the darkness. The cloud remains largely unseen, yet its structure can be reconstructed from the paths of the few members that travel close enough for sunlight to reveal them. Deeper within the Oort Cloud, the middle reservoir contains bodies that remain far beyond the directly observed planetary regions, but are held more securely by the Sun than objects in the outermost zones. Their orbits can still extend across many thousands of astronomical units, and a single revolution can require hundreds of thousands or millions of years. At these distances, sunlight is extremely weak, temperatures remain low, and physical change proceeds slowly. Yet the gravitational connection to the Sun is stronger than it is near the remote fringe, making this region more resistant to the slow stripping effects of passing stars and the larger gravitational field of the Milky Way. The middle cloud does not have a sharply defined inner or outer boundary. Astronomers use dynamical behavior rather than a visible edge to distinguish broad regions. Objects here occupy orbits large enough to feel external influences over long periods, but small enough that the Sun usually retains control, even when the surrounding galactic environment changes. This makes the population comparatively stable on the scale of the solar system's age, although individual trajectories can still evolve. The region is therefore neither completely protected nor easily disrupted. The orbits are expected to remain highly varied. Many bodies follow elongated paths, carrying them through enormous changes in distance from the Sun. Their inclinations can differ greatly, so the population continues to occupy a broad three-dimensional volume. Some orbits pass above the planetary plane, others below it, and many are tilted at angles that bear little resemblance to the orderly arrangement of the major planets. This spread preserves the spherical character of the wider cloud, while reflecting the long history of scattering and external perturbation. At the farthest portions of these orbits, motion becomes very slow. A body near aphelion, the point farthest from the Sun, can remain in that remote part of its path for an exceptionally long time. The object is still moving, but its speed is small compared with the velocities of planets near the Sun. Solar gravity continuously bends the path back inward, and the body eventually begins its long return. Because the orbit is so large, the difference between one passage and the next can include changes produced by galactic tides and distant stellar encounters. The middle Oort cloud is expected to contain primitive material left from the early solar system. The bodies probably include mixtures of frozen water, carbon-bearing compounds, silicate minerals, and other substances that condensed or accumulated when the Sun and planets were young. They are not thought to have formed at their present distances. Instead, many likely originate much closer to the giant planets and reach the cloud after gravitational encounters alter their orbits. Their present location is therefore a record of migration rather than a birthplace. This history leaves the objects physically cold but dynamically complex. A small body may preserve ancient material while traveling on an orbit reshaped many times by gravity. Its surface can be modified slowly by cosmic rays and energetic particles, while deeper layers remain better protected. With little solar heating, there is usually no strong cometary activity. Gas and dust do not form a large surrounding coma under ordinary conditions at these distances. The body remains dark and difficult to detect, reflecting only a tiny amount of the already faint sunlight. Direct searches for middle cloud members face severe observational limits. Brightness decreases strongly with distance, because sunlight must first reach the object and then reflect back toward a telescope. A body only a few kilometers across becomes effectively invisible long before reaching the distances typical of this region. Even much larger objects would be difficult to identify unless they happen to possess favorable size surface properties and orbital position. As a result, the middle cloud is reconstructed mainly through dynamics rather than direct imaging. Long-period comets provide part of that reconstruction. When one of these bodies is perturbed onto a path with a smaller perihelion, it can eventually approach the inner solar system. Its motion can then be measured and its previous orbit estimated. Some of these reconstructed trajectories indicate origins at enormous distances, while others suggest more tightly bound reservoirs. The observed sample remains incomplete because only a very small fraction of the population ever enters a region where telescopes can find it. The greater binding of middle cloud objects changes how external forces affect them. Galactic tides still act, but the same disturbance generally produces a smaller orbital change than it would for a body farther outward. Passing stars also remain relevant, yet most encounters cause modest adjustments rather than immediate escape. The Sun's gravitational control has become stronger simply because the objects are closer. This gradual change in stability illustrates why the Oort cloud is best understood as a continuous distribution rather than a set of sharply separated shells. The density of bodies may also increase inward, although the exact profile remains uncertain. Dynamical models often produce larger numbers of surviving objects at more tightly bound distances because those orbits are harder for external forces to remove. The true population depends on the early architecture of the giant planets, the history of planetary migration, the Sun's birth environment, and billions of years of galactic perturbations. Different assumptions can lead to different estimates, so the number of bodies in this region is not known precisely. Despite that uncertainty, the middle Oort cloud occupies an important part of the solar system's distant structure. It contains objects that are remote enough to remain almost completely unseen, yet bound strongly enough to survive for very long intervals. Their orbits preserve evidence of the gravitational processes that shaped the young planetary system, while their cold interiors may preserve material from that same era. Across this region, the Sun's influence becomes steadily more secure, and the distant cloud changes from a fragile outer population into a more durable reservoir of ancient, icy bodies. The enormous spacing between these objects also means that collisions are expected to be rare. Most bodies spend their lives moving through empty space separated from neighboring members by distances larger than their own sizes. Their long-term evolution is therefore governed by gravity rather than frequent impacts. The quietness of the environment helps preserve the cloud as a dispersed archive altered slowly by orbital forces instead of continual physical encounters. Moving inward through the Oort cloud, the character of the distant population begins to change gradually rather than abruptly. The broad, nearly spherical distribution of the outer reservoir gives way to a region where objects are more tightly bound to the Sun and increasingly resistant to weak disturbances from the galaxy. There is no visible surface marking this transition. Instead, the change appears in orbital energy stability and the growing importance of solar gravity. Bodies in this zone still occupy enormous paths, but those paths are less easily altered than the most distant trajectories farther outward. The transition is difficult to define with a single distance because the Oort cloud is not directly mapped. Astronomers describe it through dynamical models that follow how small bodies respond to the Sun, the giant planets, passing stars, and the gravitational field of the Milky Way. Different models place the change between outer and inner populations at somewhat different distances. The exact boundary remains uncertain, but the general pattern is consistent. As objects move inward, they become harder to strip away and less sensitive to small external perturbations. Orbital shape remains important in this region. Many bodies are expected to follow elongated paths, spending much of their time far from the Sun before returning towards smaller distances. Yet the size of these orbits is generally reduced compared with the broadest paths in the outer cloud. A smaller orbit means stronger average solar binding. This does not remove the influence of the galaxy, but it makes each distant disturbance less effective. A passing star that could greatly alter an outer cloud object may produce only a modest change here. The population may also become less perfectly spherical. The outer cloud is often modeled as approximately isotropic, meaning that orbital directions are distributed broadly in all directions. In the transition region, some memory of the original planetary plane may become more apparent. Objects closer to the Sun have experienced less complete randomization from galactic tides and stellar encounters. As a result, the distribution can become somewhat flattened or uneven, depending on the history of early scattering and the later gravitational environment. This gradual change carries information about how the cloud forms. Small icy bodies are not thought to originate at these distant locations. During the early solar system, gravitational encounters with the growing giant planets scatter many planetesimals onto large eccentric orbits. Some escape completely. Others travel far enough outward for external forces to modify their paths and help detach them from repeated close encounters with the planets. The transition region contains survivors of this long redistribution, preserving a mixture of solar and galactic influences. The effectiveness of external perturbations depends strongly on orbital size. Galactic tides act continuously, but they change the orbit of a more tightly bound body more slowly. Stellar passages also become less disruptive with decreasing distance. This produces a kind of gravitational shielding, not through any physical barrier, but simply because the Sun's attraction becomes stronger. A body deeper in the cloud requires a larger change in energy to be removed from solar control. The same weak impulse, therefore, causes a smaller fractional change in its orbit. These differences also affect how easily objects can be redirected towards smaller perihelion distances. In the outer cloud, galactic tides can gradually lower perihelia and send long-period comets inward. In the transition zone, that process becomes less efficient because the orbits are more compact. Some bodies can still be altered over very long periods, especially when stellar encounters and galactic tides work together, but the rate of change decreases. The population becomes more dynamically protected even while remaining remote. The physical environment stays cold and dark. Sunlight is still weak and most small bodies remain inactive. Water ice and other frozen compounds can survive for immense intervals while cosmic rays slowly alter the uppermost surface material. Collisions are expected to be uncommon because the bodies are widely separated. Their internal structure may therefore preserve early solar system material with relatively little thermal processing. The dominant changes occur in their trajectories rather than in their appearance. Because these objects are faint direct observations, provide only limited guidance. A body hundreds or thousands of kilometers across may be detectable at some extreme distances under favorable conditions, but most comet-sized objects remain far below the brightness limits of current surveys. The transition region is therefore inferred largely from the behavior of comets and from numerical simulations. These models can test how different early planetary arrangements produce different distant reservoirs and how those reservoirs evolve across billions of years. One important uncertainty concerns the original environment in which the Sun forms. The Sun likely begins its life among other stars in a stellar group or cluster, although the exact density and duration of that environment are not known. Nearby stars in such a setting could influence the earliest stages of cloud formation more strongly than typical stellar encounters in the present galactic neighborhood. The transition region may retain traces of that early history, but separating those traces from later evolution remains difficult. Another uncertainty concerns the total number and mass of bodies stored here. Models often predict a substantial population, potentially larger than the number residing farther outward because tighter orbits are more resistant to loss. Yet the true distribution depends on how efficiently planetesimals are scattered, how many survive, and how strongly external forces reshape them. Without direct detection of a representative sample, these quantities remain estimates rather than measurements. At these distances, even the meaning of a stable orbit is statistical rather than absolute. An object can remain bound for billions of years, while its orientation and perihelion change slowly. Another can occupy a similar region yet respond differently because of its orbital phase. Stability, therefore, emerges from many weak gravitational influences acting together across immense intervals. The outer to inner transition is therefore defined by a steady change in gravitational security. The Sun's control strengthens, external disturbances become less effective, and the overall geometry may begin to retain more memory of the solar system's original flattened structure. Nothing changes suddenly across a single distance. Instead, the cloud becomes progressively more compact, more stable, and more securely attached to the Sun, while still remaining part of the immense and largely invisible reservoir of icy bodies surrounding the planetary system. Within the outer reaches of the Hills cloud, the distant population becomes more tightly connected to the Sun than the objects occupying the broader spherical Oort reservoir. The Hills cloud is a proposed inner concentration of icy bodies whose existence is supported mainly by dynamical models rather than direct observation. It is expected to occupy a vast region well beyond the known planets, yet its members follow smaller and more securely bound orbits than many objects farther outward. Because solar gravity is stronger here, external disturbances from passing stars and the Milky Way act more slowly and remove fewer bodies. The name refers to a theoretical inner reservoir that may contain a large fraction of the solar system's distant cometary material. Its exact shape, size, and population remain uncertain because no complete sample has been observed. Models generally suggest that the Hills cloud could be denser than the outer Oort cloud, not because its objects are physically close together, but because more bodies may survive within each unit of volume. Even here, the spacing between individual objects is expected to be enormous, and collisions should remain rare over long intervals. The greater stability of this region follows directly from orbital energy. A body closer to the Sun is bound more strongly and requires a larger gravitational disturbance to escape. Passing stars that can easily alter objects near the far edge of the solar system have a smaller relative effect on bodies in the Hills cloud. Galactic tides still act, but their ability to change perihelion distance is reduced. The result is a reservoir that can retain objects through disturbances that gradually deplete the more distant cloud. Many of these bodies are thought to travel on elongated orbits, though their paths do not extend as far into interstellar surroundings as those of the outermost population. They may still require tens of thousands, hundreds of thousands, or longer periods to complete a single revolution. Near the farthest point of an orbit, motion remains slow and sunlight remains extremely faint. Yet the Sun's gravitational influence is stronger than in the remote outer cloud, so the path is less vulnerable to small impulses. The orbital directions may also retain more structure. The outer Oort cloud approaches a spherical distribution because long-term perturbations can randomize orbital orientations. In the Hills cloud, the weaker effect of external forces may preserve more memory of the flattened disk from which the original planetesimals emerge. Models can therefore produce a population that is neither a thin disk nor a perfect sphere. Instead, it may form a thick, extended distribution with a wide range of inclinations and an uneven concentration around the Sun. The physical bodies themselves are expected to resemble other primitive small objects of the distant solar system. They may contain water ice, carbon-bearing ices, silicate rock and complex organic material. Their interiors can remain cold for billions of years because solar heating is extremely weak. Surface layers may be processed by cosmic rays and other energetic particles, gradually changing color and chemistry, while deeper material stays less altered. Without strong heating, most objects remain inactive and do not develop the bright comas associated with comets near the Sun. The Hills cloud can also act as a long-lived storage region for bodies that are difficult to remove but not completely isolated. A passing star may change an orbit slightly without ejecting the object. Repeated disturbances can accumulate and some bodies can slowly move into orbital configurations where other forces become more effective. This process is expected to occur over very long time scales. The reservoir can therefore remain stable as a whole while individual members continue to evolve. Astronomers study this region mainly through simulations of solar system formation and through the unusual orbits of a small number of distant observed objects. Such objects do not provide a direct map of the Hills cloud because their present trajectories may have several possible explanations. Some highly detached bodies travel far beyond Neptune and remain outside strong direct encounters with the giant planets. Their existence shows that the distant solar system contains dynamically unusual populations, but it remains uncertain which observed objects, if any, should be considered direct members of the Hills cloud. The distinction matters because the Hills cloud is defined primarily as a reservoir predicted by long-term gravitational evolution. A single distant body cannot establish its full structure. Scientists instead compare populations generated in numerical models with the kinds of orbits that are observed. These models include the gravity of the giant planets, the changing positions of those planets during the solar system's youth-passing stars, and the galactic environment. The resulting distributions help estimate which regions can preserve bodies for billions of years. The Sun's birth environment may be especially important for this population. If the young Sun forms among many neighboring stars relatively close, stellar passages could help place scattered planetesimals onto stable, distant orbits before the birth cluster disperses. Such interactions could produce a more compact cloud than the present galactic environment creates efficiently. The exact role of this process remains uncertain because the properties of the Sun's original stellar neighborhood are not known in detail. Even with these uncertainties, the basic dynamical reason for an inner reservoir is strong. Bodies that are scattered far from the planets but not carried to the most weakly bound distances can survive more easily. They are less exposed to galactic stripping, yet far enough from the giant planets to avoid frequent disruptive encounters. Over the age of the solar system, this combination can preserve a substantial population. Its members may therefore preserve orbital information that has been erased more thoroughly in the outer cloud, although interpreting that record depends strongly on uncertain models of the solar system's earliest environment. The outer reaches of the Hills cloud therefore occupy a quiet gravitational refuge. The objects remain extremely distant, cold, dark, and difficult to observe, but their attachment to the Sun is firmer than that of the outer Oort population. Their survival depends on the same forces that shape the wider cloud, yet those forces act here with reduced effectiveness. In this region, the solar system's distant reservoir becomes less fragile and more enduring, preserving ancient bodies in orbits that can remain stable across much of the Sun's lifetime. Deeper within the inner Oort cloud, the distant population is expected to become more compact, more tightly bound, and more resistant to disruption. This region remains theoretical because no complete population has been observed directly. Yet numerical models consistently allow a substantial reservoir of icy bodies at distances far beyond the known planets. Compared with objects in the outer Oort cloud, these bodies occupy smaller orbits and experience stronger solar gravity. Their paths may still be enormous by planetary standards, but the Sun holds them with enough strength that passing stars and galactic tides alter them more slowly. The deep inner cloud may contain a large fraction of the bodies stored in the solar system's distant comet reservoir. Some models suggest that this region could be more heavily populated than the outer cloud, because objects on tighter orbits are harder to remove. The exact number remains uncertain. Estimates depend on assumptions about the early arrangement of the giant planets, the amount of material available for scattering the density of the Sun's birth environment, and the history of stellar encounters. Even a dense inner cloud would still be extremely sparse in ordinary terms, with individual bodies separated by vast stretches of nearly empty space. The origin of this reservoir begins during the formation of the solar system. Small solid bodies, often called planetesimals, grow within the disk of gas and dust surrounding the young sun. Many form in the region of the giant planets where temperatures are low enough for water and other volatile compounds to freeze. As Jupiter, Saturn, Uranus, and Neptune grow, their gravity strongly affects nearby planetesimals. Repeated encounters scatter large numbers of these small bodies onto new trajectories, sending some inward, some outward, and some entirely away from the Sun. A body scattered outward can acquire a highly elongated orbit. If its path still returns through the region of the giant planets, additional encounters may continue to change its motion. For long-term survival in the distant cloud, the orbit must eventually become detached enough that repeated planetary encounters are reduced. External gravitational influences can help make this possible. In the young solar system, nearby stars and the surrounding stellar environment may have changed the outer portions of scattered orbits, lifting their closest approach away from the giant planets while leaving them bound to the Sun. The deep inner Oort cloud is especially important in models that include the Sun's probable birth within a cluster of stars. Most stars appear to form in groups rather than in complete isolation. If the young sun spends part of its early life near other stars relatively close, stellar passages may occur more frequently than they do today. These encounters can alter the paths of scattered planetesimals while the solar system is still forming. Some simulations show that such an environment can create a compact inner reservoir that survives long after the original stellar group disperses. The exact conditions of the Sun's birth cluster remain uncertain. Astronomers cannot reconstruct the positions of neighboring stars from more than 4 billion years ago with precision. The cluster may have been relatively loose or comparatively dense, and the Sun may have remained within it for a shorter or longer interval. Each possibility changes the efficiency with which distant bodies are captured into stable solar orbits. The present inner cloud may therefore preserve indirect evidence of an environment that no longer exists. Once stored in this region, the bodies can remain cold for immense spans of time. Sunlight at these distances is too weak to produce the strong surface activity associated with comets in the inner solar system. Frozen water, carbon monoxide, carbon dioxide, methane, and other volatile compounds may survive beneath or within ancient surface layers. Cosmic rays and energetic particles continue to process exposed material, but they penetrate only limited depths. The interiors of larger bodies may preserve material that has experienced relatively little heating since the solar system formed. The physical structure of these objects is probably diverse. Some may be porous mixtures of ice and rock assembled gently from smaller components. Others may have experienced collisions, compression, or partial internal heating early in their history. Radioactive elements present when the solar system was young could have warmed the interiors of sufficiently large objects, while smaller bodies may have remained colder. Because no representative sample from the inner Oort cloud has been directly studied, the relative importance of these processes remains uncertain. Orbital evolution continues even in this more protected region. Passing stars can still produce small changes and the galactic tide remains present, but their effects are weaker than farther outward. A body can remain on a stable, distant orbit for billions of years without being removed. Some objects may slowly drift into configurations where external forces become more effective, while others remain deeply stored. The inner cloud, therefore, behaves as a long-lived reservoir rather than a perfectly frozen population. Its geometry may also differ from the nearly spherical outer cloud, because external perturbations are less effective here. Orbital orientations may retain more memory of the original planetary disk. The distribution may be thick and extended rather than completely isotropic. Models differ in detail and no direct map exists to determine the exact shape. What remains consistent is that stronger solar binding allows the deep inner cloud to preserve orbital structure that would be more thoroughly altered at greater distances. This region also helps explain how the solar system can retain ancient cometary material over its entire lifetime. Objects placed only slightly farther from the planets may continue to experience disruptive encounters, while objects scattered too far outward are more easily stripped away by stars and galactic tides. The deep inner Oort cloud occupies a broad gravitational middle ground where bodies can become detached from the planets without becoming weakly attached to the Sun. The result is a hidden archive of early solar system material stored on vast, durable orbits. Its members remain almost entirely invisible, and their total population is unknown, yet their expected stability gives this region an important role in models of solar system formation. Here the Sun's distant reservoir becomes more strongly protected, and ancient icy planetesimals can remain preserved for billions of years in the deep interior of the Oort cloud under exceptionally quiet and stable conditions. At the uncertain inner boundary of the Oort cloud, the solar system changes from a largely theoretical reservoir of distant icy bodies into a region where a small number of unusual objects can be observed directly. No agreed line marks the transition. Instead, the inner edge depends on orbital history, the influence of Neptune, the early arrangement of the giant planets, and the environment in which the Sun forms. Different dynamical models therefore place the beginning of the inner Oort cloud at different distances. The boundary is not a wall of material, but a zone in which the origins of individual objects become increasingly difficult to assign with certainty. The difficulty begins with the meaning of membership. An object can travel hundreds of astronomical units from the Sun and still have an orbit shaped partly by processes associated with the Kuiper Belt or scattered disk. Another body at a similar distance may have been placed on its path by stellar encounters during the youth of the solar system. Distance alone cannot distinguish these histories. Astronomers instead examine quantities such as perihelion distance, orbital size inclination, and the degree to which Neptune can still alter the path over long intervals. Neptune is central to this distinction because its gravity controls much of the distant region beyond the major planets. Bodies whose orbits approach Neptune closely can undergo repeated gravitational encounters that change their eccentricity and orbital energy. Even when direct encounters do not occur, resonances can slowly modify some trajectories. A resonance appears when orbital periods maintain a repeating gravitational relationship. These interactions can lift or lower perihelia and produce detached-looking paths without requiring an origin in the Oort Cloud. For this reason, an object must be studied dynamically rather than classified only by its present position. Farther from Neptune's effective reach, some objects occupy orbits with unusually large perihelia. They never approach the planet closely enough for ordinary scattering to explain their present paths easily. Sedna is the best-known example of this broad class. Its orbit remains far from Neptune at closest approach and extends hundreds of astronomical units from the Sun. Its existence demonstrates that the solar system contains bodies in strongly detached orbits, but it does not by itself establish a precise inner edge for the Oort Cloud. Models of the Sun's birth environment provide one possible explanation for such trajectories. If the young Sun forms within a group of neighboring stars, stellar gravity can alter the orbits of planetesimals that have already been scattered outward by the giant planets. A passing star can raise the perihelion of an object, separating it from further strong encounters with Neptune while leaving it bound to the Sun. Depending on the density and lifetime of the stellar group, this process can create an inner population beginning at a few hundred astronomical units, or in some models at somewhat smaller distances. The uncertainty in these models reflects uncertainty about the Sun's earliest surroundings. The original stellar cluster has long since dispersed, and its exact properties cannot be recovered directly. The number of nearby stars, their masses, their speeds, and the duration of the Sun's residence among them all affect the resulting distant population. A denser environment can produce stronger perturbations, while a looser environment can leave a different orbital signature. The inner boundary of the Oort cloud may therefore be partly a fossil record of conditions that existed only during the solar system's infancy. Planetary migration adds another layer of complexity. The giant planets do not necessarily remain at their original distances while the young solar system evolves. Their changing orbits redistribute small bodies and alter the locations of resonances. Some planetesimals are scattered outward repeatedly, while others become trapped temporarily in dynamical relationships with Neptune. This history can produce remote objects that resemble inner cloud members even when their origins lie within the planet-dominated region. Separating these pathways requires long numerical integrations that test whether an observed orbit can survive and how it may have formed. The inner edge is also difficult to identify because observational surveys detect only a small and strongly selected sample. A distant body is easiest to discover when it approaches perihelion, where it receives more sunlight and appears brighter. Objects with very large perihelia remain faint even at their closest points. Smaller members are especially difficult to detect. The known population, therefore, cannot be treated as a complete map. Large areas of the sky have been surveyed to different depths, and many objects almost certainly remain undiscovered. Each new, distant object can refine the statistical picture, but classification remains cautious. Similar orbits do not necessarily share identical origins. Long-term evolution can move bodies between dynamical categories and processes that act early in solar system history can overlap with those operating later. Scientists therefore use terms such as detached object, extreme trans-Neptunian object, or inner Oort Cloud candidate according to context and the criteria of a particular study. The terminology reflects real uncertainty, rather than a failure to define a simple physical edge. Physically, these bodies remain cold, ancient remnants. Their surfaces may contain water, ice, methane, complex carbon-bearing material, and silicate rock, depending on where they originally form and how they evolve. Sunlight remains weak enough that most do not show sustained cometary activity. Their colors and reflectivities can offer clues to surface composition, but those properties cannot uniquely reveal their birthplace. Radiation processing and impacts can modify surfaces over billions of years while leaving orbital history hidden. Even a stable orbit does not reveal when the object entered this region. A body can remain detached for billions of years after a brief early disturbance, while another can reach a similar path through slower evolution under planetary and stellar gravity alone. The uncertain inner boundary is therefore a region where observation and theory meet without producing a single dividing line. The Sun clearly controls the orbits, but several different mechanisms can place bodies there. Neptune planetary migration, early stellar encounters, and long-term gravitational evolution can leave overlapping signatures. Rather than ending at one measurable distance, the Oort cloud becomes progressively harder to distinguish from other distant populations as the journey continues inward. Its inner edge is best understood as a dynamical transition defined by competing histories and incomplete observations rather than by a visible structure in space. Inside the uncertain inner boundary of the Oort cloud lies a population of distant objects whose orbits remain largely detached from direct encounters with Neptune. These bodies occupy a broad transition between the theoretical inner cloud and the more clearly planet-shaped regions farther inward. Their paths can carry them hundreds of astronomical units from the Sun, while their closest approaches remain too distant for ordinary repeated scattering by Neptune. This separation makes them valuable tracers of the gravitational history of the outer solar system, although their exact origins remain uncertain. A detached object is generally understood as a small body whose perihelion lies far enough beyond Neptune that close planetary encounters no longer dominate its present orbit. The term describes dynamical behavior rather than composition. Such an object may contain mixtures of rock water, ice, methane, and other frozen compounds, but what distinguishes it is the way gravity shapes its motion. Its orbit may be highly elongated, strongly tilted, or both, yet it can remain isolated from the strongest direct perturbations of the outermost major planet. Sedna is one of the clearest examples of this type of distant body. It follows an extremely elongated orbit, travelling far beyond the region where Neptune can scatter it during ordinary close approaches. Its perihelion remains well outside Neptune's orbit, and its aphelion extends hundreds of astronomical units from the Sun. Sedna, therefore, spends most of its long orbital period in deep, cold darkness. The object is visible only because it is relatively large and because telescopes can detect it during the portion of its orbit when it is nearer the Sun. The existence of such an orbit creates a dynamical problem. Neptune alone cannot easily place a body on a Sedna-like path while also raising its perihelion so far from the planet. Several mechanisms can produce detached orbits under different conditions. Early encounters with neighboring stars can lift perihelia after bodies are scattered outward. Interactions within the Sun's birth cluster may produce similar effects. Long-term resonances with Neptune can also modify some distant trajectories, although they do not explain every extreme orbit. More distant planetary or stellar perturbations have also been examined in models, but observational evidence does not establish a single universal mechanism. Because multiple processes can create similar present-day orbits, no detached object carries a simple label of origin. Scientists examine entire populations rather than relying on one body. The distribution of perihelion distances, semi-major axes inclinations and orbital orientations can be compared with numerical simulations. If enough objects are discovered, patterns in those distributions can reveal which formation pathways are more plausible. At present, the observed sample remains small and strongly affected by survey biases, so many interpretations remain provisional. Detection itself is difficult. A distant object shines only by reflected sunlight, and brightness falls rapidly with increasing distance. Small bodies become extremely faint long before they reach the far ends of their orbits. Surveys are therefore more likely to find objects when they are near perihelion. They are also more sensitive in some regions of the sky than others because telescope coverage weather observing seasons and limiting brightness vary. The known sample is therefore not a simple census of everything that exists. This selection effect can create apparent patterns that require careful testing. If several discovered objects seem to share similar orbital orientations, the similarity may reflect real dynamics, observational bias, or a mixture of both. Astronomers model where surveys have looked and how faint an object could have been detected in those fields. Only after correcting for such effects can the orbital distribution be interpreted more reliably. The process remains difficult because many past surveys were not designed specifically to measure the most distant populations. Detached objects also preserve information about the migration of the giant planets. Early in solar system history, Neptune and the other giant planets can move from their original positions as they exchange angular momentum with large numbers of planetesimals. This migration changes resonances and scatters material across the outer system. Some bodies can be placed on distant eccentric paths and later become detached from direct encounters. The details depend on how rapidly the planets migrate, whether their motion is smooth or irregular, and how much material remains in the primordial disk. The Sun's stellar environment can modify this picture further. A nearby star passing during the early cluster phase can raise the perihelion of an already scattered body, preserving it on an orbit that Neptune can no longer reach. Such a process is especially effective when the young solar system contains abundant planetesimals and neighboring stars are closer than they typically are today. The strength of this explanation depends on uncertain details of the Sun's birth environment, so detached objects offer one of the few remaining ways to test those ancient conditions indirectly. Some members of this region may occupy stable orbits for billions of years. Others can evolve slowly because of weak resonances, galactic tides, or distant stellar perturbations. Their long-term behavior depends strongly on orbital size. Objects with smaller semi-major axes remain more securely controlled by the Sun and planets, while those with larger paths become increasingly sensitive to external forces. The detached region, therefore, contains a gradient rather than a single dynamical category. Physically, these bodies remain among the coldest preserved remnants of planetary formation. Their surfaces can be altered by radiation impacts and the slow loss or movement of volatile substances, while their interiors may retain primitive material. Large objects can experience some internal differentiation or thermal evolution, but smaller ones may remain comparatively unchanged. Their composition cannot be inferred from orbit alone, and each distant body can carry a different history of formation and surface processing. Their slow motion makes each discovery a record of conditions preserved across the entire age of the solar system. The detached population forms a bridge between the hidden inner Oort cloud and the more strongly planet-shaped regions closer to Neptune. It is defined not by a single distance, but by the weakening of direct planetary scattering and the persistence of long-lived remote orbits. These bodies remain observable clues scattered across a vast volume, each preserving part of a gravitational history that began when the giant planets, neighboring stars, and countless small bodies were still settling into the architecture of the solar system. Much farther inward than the Oort Cloud, the solar system has another boundary that is easier to describe physically, because spacecraft have crossed it. This boundary is the heliopause, the region where the outward flow of charged particles from the Sun becomes balanced by the surrounding interstellar plasma. It marks the outer limit of the heliosphere, the enormous bubble created by the solar wind. Unlike the distant gravitational frontier of the solar system, the heliopause is not defined by whether an object remains bound to the Sun. It is defined by the behavior of plasma magnetic fields and energetic particles moving through space around the star. The solar wind begins in the Sun's outer atmosphere. Hot charged particles escape continuously and stream outward in all directions, carrying part of the Sun's magnetic field with them. Near Earth, this flow moves rapidly and strongly influences the space environment around the planet. As it travels farther outward, however, it spreads across an ever larger area and interacts with material between the stars. The surrounding interstellar medium is thin, but it contains its own plasma magnetic field, neutral atoms, dust, and cosmic rays. The heliosphere forms where these two environments meet. The heliopause does not sit at one fixed distance from the Sun. Its position changes because the pressure of the solar wind varies with the Sun's activity, while conditions in the surrounding interstellar medium are not perfectly uniform. The boundary is also not expected to be a perfect sphere. The Sun moves through the local interstellar environment and the heliosphere responds to that motion. Its exact shape remains an active area of research because only a small number of spacecraft have sampled the region directly. Before reaching the heliopause, the solar wind passes through another important transition called the termination shock. At this shock, the outward plasma flow slows from supersonic to subsonic speeds relative to characteristic waves in the plasma. The region beyond the termination shock and inside the heliopause is called the heliosheath. There the solar wind is slower, hotter, and compressed as it approaches the outer boundary. The structure is shaped by magnetic fields and by interactions with particles arriving from interstellar space. Voyager 1 and Voyager 2 provide the clearest direct measurements of this distant environment. After traveling outward for decades, both spacecraft crossed the heliopause and entered interstellar plasma. Their instruments detected changes in particle populations and magnetic conditions that indicated they had moved beyond the region dominated by the solar wind. These crossings represented entry into interstellar space in a plasma sense, but the spacecraft remained deep inside the Sun's gravitational domain. They did not leave the solar system in the broader gravitational meaning of that phrase. This distinction reveals the enormous difference between the heliosphere and the Oort cloud. The heliopause lies at a distance measured in roughly hundreds of astronomical units, while the Oort cloud may extend tens of thousands of astronomical units from the Sun. An object can therefore travel far beyond the solar wind bubble and still remain on a solar orbit for millions of years. Interstellar plasma can surround it while solar gravity continues to determine its path. The solar system has several meaningful boundaries because different physical influences fade at very different distances. Neutral atoms illustrate this overlap. Because they carry no electric charge, some interstellar atoms can pass through magnetic boundaries that redirect charged particles. Neutral hydrogen and helium from the local interstellar medium enter the heliosphere and travel inward before interacting with sunlight plasma or planetary environments. At the same time, charged particles from the solar wind are increasingly slowed and redirected near the heliopause. The boundary is therefore selective rather than a solid barrier. Magnetic fields complicate the transition further. The solar wind carries the Sun's magnetic field outward, forming a vast magnetic structure throughout the heliosphere. The interstellar medium has a magnetic field of its own. Near the heliopause, these fields interact with plasma on both sides of the boundary. Their geometry can influence how energetic particles move and how the outer heliosphere is shaped. Measurements from the Voyager spacecraft have provided direct evidence, but the global structure must still be inferred from limited observations and models. Cosmic rays also respond to the heliosphere. Many high-energy particles originate beyond the solar system and travel through the galaxy. The magnetic fields and solar wind inside the heliosphere reduce the number of lower-energy galactic cosmic rays that reach the inner planetary system. Beyond the heliopause, Voyager instruments detect a different particle environment, with galactic cosmic rays becoming more prominent and particles associated with the solar wind declining. The change is gradual and complex rather than an absolute separation between two perfectly isolated regions. The location of the heliopause also changes over long time scales as the Sun moves through different parts of the interstellar medium. A denser surrounding environment could compress the heliosphere, while a lower external pressure could allow it to expand. The Sun's own activity varies as well, creating shorter-term changes in the solar wind pressure. The heliosphere therefore breathes and changes rather than remaining frozen at a single radius. Despite this variability, the heliopause provides a useful physical marker because spacecraft can detect it directly. Instruments can measure plasma density, energetic particles, and magnetic fields on both sides. This makes it fundamentally different from the Oort cloud, whose structure is inferred from distant comet orbits and dynamical calculations. The heliopause is a boundary in flowing material. The Oort cloud is a population of gravitationally bound bodies. Even at the heliopause, sunlight remains present. Although far weaker than near the planets, photons continue outward independently of the solar wind, so the end of the plasma bubble does not mark a corresponding edge for the Sun's visible light. At this distance from the Sun, the planetary system is still far inside the larger architecture of solar gravity. The heliosphere may end, but the Sun's attraction continues outward through a volume thousands of times greater in radius. The crossing of the heliopause therefore marks the end of one solar influence, not the end of every solar influence. The solar system becomes interstellar in its plasma surroundings while remaining solar in its gravitational organization, demonstrating how several different definitions of an edge can coexist around the same star. Inside the heliosphere's outer boundary, the distant solar system becomes more familiar because telescopes have directly observed large populations of icy bodies beyond Neptune. The two most important regions here are the scattered disk and the Kuiper Belt. Both contain remnants from the early formation of the planetary system, and both lie enormously closer to the Sun than the Oort Cloud. Their objects are cold, small, and often difficult to detect, yet their orbits are compact enough that modern surveys can map thousands of members and study the structure of the region in detail. The Kuiper Belt forms a broad zone beyond Neptune, extending across a comparatively narrow range of distances when measured against the scale of the Oort Cloud. It contains many small icy bodies along with dwarf planets, such as Pluto, Haumea, and Makemake. These objects orbit the Sun on paths that generally remain much closer to the plane of the planets than the nearly spherical orbits expected in the outer Oort cloud. The belt is therefore more disk-like, preserving a stronger connection to the flattened structure of the original protoplanetary disk. Within the Kuiper Belt, orbital patterns reveal the continuing influence of Neptune. Some bodies occupy relatively stable paths that avoid close encounters with the planet. Others are trapped in orbital resonances where their periods maintain repeating relationships with Neptune's orbit. Pluto is one example, completing 2 orbits around the Sun for every 3 completed by Neptune. This resonance protects Pluto from close approaches even though the 2 orbital paths overlap in distance. Similar relationships shape many other objects throughout the belt. The Kuiper Belt is not uniform. Some members travel on orbits with low inclinations and modest eccentricities, while others follow more tilted and elongated paths. These different populations likely preserve evidence of early migration among the giant planets when Neptune moves outward during the youth of the solar system. Its gravity can capture, scatter, and rearrange smaller bodies. The present architecture therefore reflects not only where objects formed, but also how planetary orbits changed after formation. Beyond the more stable belt lies the scattered disk. Objects in this region usually have more eccentric and inclined orbits, and many continue to experience significant gravitational influence from Neptune. A scattered disk body can approach the region of Neptune at perihelion and then travel far outward before returning. Repeated encounters can change its orbital energy and direction over long periods. Some members can eventually be sent inward, while others can be pushed onto wider orbits or even ejected from the solar system. The scattered disk is therefore dynamically active, compared with the more stable parts of the Kuiper Belt. Its objects do not occupy one clean ring or shell. Instead, they follow a broad range of overlapping trajectories shaped by Neptune's gravity. Some orbital paths extend hundreds of astronomical units from the Sun, but they remain far smaller than the enormous orbits associated with the Oort Cloud. Their long-term evolution is controlled mainly by the giant planets rather than by galactic tides or passing stars. This difference in controlling forces marks an important change in scale. In the Oort cloud, the Sun holds bodies so loosely that the Milky Way and nearby stars can gradually reshape their orbits. In the scattered disk and Kuiper Belt, the Sun's gravity is much stronger, and Neptune becomes the dominant external influence on many small bodies. The surrounding galaxy still exists, but its gravitational effect is negligible compared with the immediate architecture of the planetary system. The physical composition of Kuiper Belt and scattered disk objects is also easier to investigate. Because many are relatively close, telescopes can measure their brightness, colors, rotation, and in some cases, surface composition. Water, ice methane, ice nitrogen ice, and other frozen compounds appear on different bodies. Surfaces can be darkened or reddened by radiation processing of carbon-bearing material. Larger objects may retain atmospheres temporarily near perihelion, while small bodies generally remain airless and inactive. Pluto provides a clear example of the complexity possible in this region. It has glaciers of nitrogen ice mountains made largely of water ice and a thin atmosphere that changes as its distance from the Sun varies. Other dwarf planets show different combinations of ice rock and surface chemistry. These worlds demonstrate that the region is not merely a collection of identical frozen fragments. Size composition, internal heating collisions, and orbital history can produce a wide range of physical states. Collisions have also shaped the Kuiper Belt. In the early solar system, the region contains far more material than it does today. Bodies collide, grow fragment, and exchange material. Some families of objects may share a common origin in ancient impacts. Over time, planetary migration and gravitational scattering remove large amounts of mass. The present belt is therefore a depleted remnant of a much more massive primordial disk. Comets provide another connection to this region. Many short-period comets are thought to originate among scattered populations beyond Neptune. Gravitational interactions can gradually redirect some bodies inward, where further encounters with the giant planets shorten and reshape their orbits. Once they approach the Sun repeatedly, heating releases gas and dust from their surfaces, producing the familiar appearance of an active comet. Their source region is much closer than the distant reservoir that supplies many long-period comets. The Kuiper Belt also shows how misleading the phrase edge of the solar system can be. Neptune is the outermost major planet, yet an extensive population continues far beyond its orbit. The heliopause lies farther still, and the Oort